Right, so we just talked about the first law of thermodynamics, and we saw that if we're looking at a particular system, the change in internal energy depends on the amount of work done on or by our system, and the heat that is either received or removed from our system. So in this video, we're going to be interested in different processes, so particular processes that will bring our system from one state to another. And here we're going to start by looking at what we call an isobaric process. So isobaric contains, so iso, that's going to be something that we see a lot. Iso means the same, so that's the Greek root for the same, and baric, you may recognize or not, but it has the word bar in it, so which is a unit of pressure. So baric relates to pressure. So isobaric means that we're looking at a process that is happening at constant pressure. Okay, and so for a process at constant pressure, we can calculate, and we're not going to go through all of the details of how this works, but the work done by, in this case, an expanding gas. So you have here, if we look at this picture here, you can see that we start over here with an initial volume, okay? And then our gas is going to expand. So that's why you can see our piston moving to the right, so that we end up with a final volume here, which is greater than what we had initially. Okay, and so if we want to find out, the amount of work that this took, well, we can look at. It's actually not too. You can do it given what you know about our definition of work. So if you think about it, we would look at the force that is needed, okay? And we know that this force is related to pressure and area, okay? So if we look at here, um, the displacement, all right, the amount of work, remember, would be force times displacement, all right? So the displacement would be this delta x over here, and then that would be multiplied by the force. But force is related to pressure, because pressure, so if you remember, the pressure we define as force divided by area, right? So in this case, the area would be what I have here, right? So it's the cross-sectional area of my piston. So this will tell me that my force is going to be the pressure times the area. So when I calculate the amount of work is going to be force times the displacement, all right? So we're using all stuff from that previous unit on energy, okay? So now I know that this can be related to, so my force is my pressure times my area, okay? And then I multiply that by delta x here, my change in my displacement essentially. And you can see that A times delta x, you may see that that means that I'm multiplying this part by this. That's actually my change in volume. So that's going to be pressure times the change in volume. Okay, so that's the amount of work that's going to be done by my gas. And so this is interesting in terms of how we can relate that to the first law, because in the first law we have to use any heat that is any energy that's being exchanged, either by gaining heat, for example, or losing heat, or by any work that's being done. So in this case, the gas is doing work, and that means that we would have to subtract the internal energy that we had initially from that amount of work to find the final value. Okay. So now this could be combined with different things. We could be adding heat so that the gas is expanding, for example. But this is a particular process because it is happening at constant pressure. So now there's something that you will see in the textbook, which is used a lot when we're looking at different processes, and that's what we call a PV diagram. So PV diagram means that we are um, looking at pressure versus volume. Okay, so in this particular process, we're keeping our pressure constant. So that's why we have a flat line over here. So we're going from my initial volume to the final volume, but at constant pressure. So this is beyond what you need to know for this class, but I know some of you may be moving on to another physics course or may just be interesting, but you may know that this here, if I multiply P by, so P, which is the value that I have here, right? That's my pressure, times, so this is what I have here. That's my pressure. I multiply that by my change in volume, which is what I have over here, right? So V final minus V initial, so that's my delta V. As it turns out, that corresponds to the area under my curve from the PV diagram. So this is something we can see on this simpler example, but as it turns out, that works anytime. So you could draw your PV diagram, look at what the pressure versus the volume looks like, and by calculating the area under this curve, you can find the work done. If you lost me there, don't worry at all about that. It's just if you were noticing that this is a nice rectangle, and we can easily calculate the area. It is actually something that is proven to mathematically work. All right, so but in an isobaric process, what you should remember is that the work is going to be that pressure at which the process is happening times the change in volume. All right, next one, isochoric process. So iso, it tells you that we're going to keep something constant again. So same, and choric is in this case a constant volume. Okay, so in this case, we're keeping a constant volume. If you just follow what I was just telling you about the PV diagram, all right, so P versus V, if I now keep the volume constant, then let's say we're going from, so we keep this constant volume and we're going to change the temperature, the pressure, and as it turns out, we're going to change the temperature also. But we have a vertical bar. So if we were to look at the area under this curve, this is actually 0. And if the volume remains the same, as it turns out, the work done is going to be equal to 0. So if there's no change in volume, the work done is equal to 0. And so in this case, the pressure is going to change because you're adding heat, for example. But because the volume did not change, so that means that you have a container that is not with one of those movable piston and it sticks to its volume, then there's no work being done. So that's an easy calculation for this one. But you can see, by the way, that now, if you look at the amount of heat that's being added and the work is being equal to 0, you can apply that to the first, you can apply your first law to find the change in internal energy. All right, an adiabatic process. I will post a video of an example of an adiabatic process that I think is fun and you could actually do at home. So look for that in Canvas. I'll put it after this video. An adiabatic process is one for which we're going to have no heat flow. So adiabatic means that Q is going to be equal to 0. So typically that means that you either have a system that is very well insulated. So that means that no heat can come in or out. And sometimes, because that's actually really difficult to do, you can actually have the process happen really fast. So in the video that I will post, that's what happened. So we changed, we're going to essentially create a little cloud through an adiabatic process, but we're going to make it happen really fast so that there's no change, no time for heat to be exchanged, essentially. So in that case, it means that all of the change in internal energy of our system is going to come from the work done on or by the system. So here you have an example where you can see that we put insulation around our system. Okay. In this case, we're doing work, so we are pushing down, and so work is being done on our system, and the gas is being compressed, which leads to an increase in pressure and an increase in temperature. Okay, so just remember, work is being done on the system, so that means that we count that W as negative, which means that it's a positive change in internal energy, right? So it's going to increase the energy because we're providing the work in that case. Now, if you let it expand, now work is being done by the system, it's going to come out to be um, a loss in internal energy because the work needed to come from somewhere and it's coming from that internal energy. This is an example of an adiabatic process because it's happening really fast. So instead of having the system being insulated, we're just going to make it happen really quick. So in this case, so that's not the video I'm going to show you. We're actually going to do the opposite, or not the opposite, but here you would have something at room temperature. And what you're going to do is compress it really, really fast. And so there's no heat flow in or out of our system. That essentially gets you an increase in pressure and temperature, and you can actually set this on fire. I have not tried this one, but what we're going to do instead is have some vapor in a bottle. And essentially, so what I do is I compress it with a pump in. So in the bottle, I put very high pressure, and then also then open it and bring it to atmospheric pressure, and you'll see the effect. And you can do that at home pretty easily. All right. So just a summary to show you what we've seen in this video. We saw an isobaric process, so constant pressure. So this is what we saw, right? And if we put that in the first law, that's the consequence for the first law of thermodynamics. Constant volume, we say that there's no work done, so the change in internal energy is due to heat only. Isothermal process, this is not one we talked about, so I want to mention it here. For constant temperature, that means that the change in internal energy is equal to 0. That's because we said that internal energy is purely temperature dependent. So if we don't change the temperature, right, so isothermal, constant temperature, then there's no change in internal energy. So that means that whatever amount of work is being done is going to have to be equal to the amount of heat that's being exchanged. Okay, because overall, that means that the internal energy of our system remains the same. So finally, adiabatic process. So this is where we said Q is equal to 0, and that means that any work that's being done is going to be affecting the change in the internal energy directly. All right. So those are a lot of different processes that can happen. And you can see that you can, for each one, relate or figure out a way to find either the work, the heat exchange, or the change in internal energy, and then you can relate that to the other forms of energy by applying the first law of thermodynamics. And it's all coming from, again, this idea that energy is conserved, so it's not disappearing, it's going to show up somewhere else in a different way. Moving on, we're going to be talking about the second law of thermodynamics. That's going to be one that's going to be very important when we start talking about engines, which will be the next application. All right, so stay tuned, and we'll talk about the second law next. Thanks. Bye.